Hello and welcome to the second session of our Formula Student Workshop by SimScale and Formula Student Germany. Yes, today, we are gonna dive into the details of computational fluid dynamics and talk about the difference between average simulation and a good simulation that you can use to develop your car. Yes, I'm very happy and proud to see that again so many people have joined. Seemed like you enjoyed our first session. And actually, before we start with the session, I would like to make sure that everybody can hear me loud and clearly. You should know this procedure from our last session. So you will find a button in your control panel called Raise Your Hand. And please raise your hand in the case you can hear me now. Great, I already see some hands. Okay, seems like everything is working fine. Perfect. In the case you want to use the alternative or toll-free audio service number, just dial one of the numbers you can see right now on your screen. All of them are toll-free if you call them, and then access following code 991502345 when you are asked. Great, then let's take a look at our today's agenda. And don't worry, today it won't take us 2 hours. And as I mentioned, we will talk about complete car aerodynamics today. And if you remember, last week we had this great introduction to the fundamental of aerodynamics, which was very general by René Hilhorst. And today we want to adapt some parts of the knowledge he shared with us and show you how you can apply this to your simulation. And we will talk about how CFD is actually working, so what's the fundamental idea behind it. We will talk about the different components which have the impact on the quality of the CFD result, and I will show you some very important modeling techniques that you will need to create a simulation of your race car, including all the small side effects like radiator, rotating wheels, etc. Just after that, we have a live demo where I will show you how to set up this kind of simulation on your own. And then we will have time for a Q&A, and I will show you your homework. Together with me today is also one of my colleagues. He will help you in the chat. So if you have questions, just ask it through the question chat window, and we will ask them immediately in the chat or discuss them at the Q&A if the question is relevant for a larger audience. Great, let's start. And first of all, we just have to talk very briefly about some organizational stuff. So this is the second out of 4 sessions. And last week we had the introduction to aerodynamics. Today we will talk about complete car aerodynamics. And next week we will have Torbjörn Larsson joining as a guest speaker who will explain how you can use CFD and how to integrate CFD to your development process. And the week after, last week, Nicholas Pfeiffer will join, who is the CFD team leader at eMotorsport Cologne, and he will show you a case study and explain how he used SimScale and the last year's simulation course to implement a CFD and aero development process at eSport Cologne. Let's also talk a little bit about some organizational things of this workshop, because I received a lot of emails last week from people who had questions regarding that. So this workshop is basically made of 2 components. We have a live webinar, which is also recorded, and we will provide you with the recording. And during this live webinar, we will teach you the most fundamental concepts. And the second part is a voluntary homework assignment. And this homework assignment is about setting up your simulation on your own. And it will help to deepen the knowledge you've gained. And additionally, you can share this homework using a form on simscale.com. And every participant who will submit all 4 homeworks will receive a certification from us. And let's also talk about some questions which were really asked a lot of times. So first of all, yes, we will record the workshop sessions, the webinar session, and provide you with the recording. And in the case, and that's maybe the most important question, in the case you need support with your homework assignment, please use the forum. The tutorial itself is provided as a forum topic in our SimScale forum, and you can directly react to this tutorial in the case you have problems, explain your problems maybe at a project link, and you will receive help very, very quickly. All right, then I think we can start now, and yes, let's talk about advanced CFD modeling. And if you have questions, just write them into the question window. Okay, and first of all, I would like to talk about CFD in general. And last week, I already tried to explain what is the fundamental idea of CFD. But let's dig into this topic more detail today. So CFD stands for Computational Fluid Dynamics, which you can translate also like a kind of virtual wind tunnel. And a lot of people asked me the first time I tell them about CFD and the great opportunity CFD is providing to the users. They asked me, what is the CFD result actually? How can I imagine a CFD result? And so let's pick up this question, and let's imagine you want to run a CFD simulation of a wing, a multi-element wing. And the gray box around this wing is our virtual wind tunnel, our flow domain. And actually what the CFD simulation should deliver is a velocity and the pressure field for the whole domain, which means that we want to know the velocity in this gray fluid domain at any point for every time step. And the same for pressure. So the result is a vector field of velocity, which is depending of space and time, and a scalar pressure field, which is also depending on space and time. And there are good and bad news. Actually, the good news is more than 200 years ago, several scientists independently developed the so-called Navier-Stokes equation, which is completely describing the behavior of a fluid substance and how energy, momentum, and mass are conserved in a fluid substance. And unfortunately, there are also some bad news. Nobody until now found a way to find a general valid analytic solution for this equation. So we know basically how this equation is looking like and what it is expressing, but we cannot solve it analytically, only for a very few simple cases. And let's go back to our example. If we now try to find a solution for this example, for this equation describing our wing example and our virtual wind tunnel, we won't found any solution. But there is some hope, because on the other hand, it's possible to apply this equation on very simple phenomena and very simple shapes. For example, on a hexaeder element. And if we apply this equation to the simple hexaeder element, we will get basically two equations or three equations depending on our simulation. And if we say it's isotherm, so we don't expect the density and temperature of the flow to change, it will lead us to two equations which are describing the conservation of mass and the conservation of momentum inside this fluid element. And here on the right side, you can basically see how these equations are looking like, and it's looking very complex. But don't worry, because actually the meaning of this equation is quite simple. It just says that if we take a look at what is happening inside and at the boundaries of this element, the rate of change of mass inside this element must be equal to the difference between the ingoing mass fluxes and the outgoing mass flux. And the same for the momentum. The rate of change of momentum inside this volume is defined by the difference between the incoming momentum and the outgoing momentum. And now you ask yourself maybe, okay, that makes sense, but how can this help me? Well, just imagine you can't solve or even not write down this equation for this very complex case, but for the easy one. So what can you do? You can replace your complex problem by a system of very small problem, which means you divide your fluid domain into a lot of small pieces of volume. And then we can apply this equation to all the small volumes, and we will receive a submodel which is representing our problem based on this small finite volumes. And it's still not the solution that we're looking for, because right now we still have this differential equation second order we cannot solve, but there's something very nice we can do, because if we apply the so-called divergence theorem or Gauss theorem, which I'm quite sure heard in the past at university, it can help us. The divergence theorem is, in the end of the day, it's just giving a relation between what is happening, or between the flux around a closed surface and the volume this closed surface is containing. And if we apply this, it helps us on two ways. First of all, it helps us to calculate phase values in terms of cell-centered values, because if you think about it, we are just, in the end of the day, we're averaging everything which is happening here. And the second and most important effect is, if we apply this and integrate it, it will transform our partial differential equation into a linear equation system, which we can solve. And as you might know from college, university, or school, solving linear equation systems can be very exhausting. But the big advantage is that here computers can help. And basically, what we're doing at CFD is that, if you remember at the live demo and the homework we did last week, we are first of all dividing the domain by creating the mesh. Then we are integrating over the cell, which just gives us a linear equation system, which we are solving iteratively. And this is, in the end of the day, the idea and process of CFD. And this is a process which is similar in the end for most of simulation techniques. So you have fundamental equations which you can not apply or not solve. Then you transform them and into a linear equation system using numerical schemes like finite volume method, which is based on the idea of CFD, but you can also use other methods like finite element analysis or finite element method. And in the end of the day, you can solve linear equation system. And this will give you a result. And this result, you have to use it carefully because of two reasons. First of all, since you replaced your fluid domain by a lot of small structures, it's a simplification. And the result depends on how you discretize your domain. And this image is showing it very, very clearly. In the end, we are calculating a value for pressure and velocity for each cell volume. So the accuracy of our simulation locally is depending on the size of these elements. And we should use smaller elements where we have higher gradients, and where we have low gradients, we can also use larger elements. And that's the first thing you have to consider. The second thing is that, independent from the fact that we now get a discrete solution, so only for the defined point and not for all points in the continuum, even the results in the cells are just an approximate solution. And every time you use CFD, you have to keep this in mind. And now let's take a look at some components of a CFD simulation. And I choose this terms or components because they are used in a lot of books. A lot of CFD tools are also using these words for describing different parts of the simulation process. And I just want to go with you through this different stuff and discuss the meaning and the impact on the CFD result. And first of all, as you know, we need a mesh. And maybe one general thing before we talk about meshes. In the end of the day, CFD can mean computational fluid dynamics or colorful desktop. What I want to point out with that is that a CFD simulation can also give you total wrong results And it's very important to understand when you can trust the result and also how to make sure that your result, your approximation, is exact enough for your problem. So let's talk about the different simulation components. And the very first and also a very important component is the mesh. As I told you, we need the mesh to discretize our fluid domain. And in the end of the day, we are telling the solver or the CFD tool with the mesh where we want which kind of accuracy. And therefore, the mesh is very important. And basically, there are two things. First of all, we want to make the mesh as small as possible because a larger mesh means longer computation time and needs more computational resources. But on the other hand, we want that our result is as accurate as possible. Therefore, this is a trade-off. And the perfect mesh is as small as possible and as accurate and fine as necessary. And since there is not one single solution, here we should refer to a concept called mesh independency, which means if you do a CFD simulation, for example, of front wing, and let's say use a uniform mesh, which means you have everywhere the cell same size, and you would start now to refine the mesh and like compare, let's say, the same simulation setup, the same problem with 10 different meshes which have different levels of fineness, then you would see that at the beginning when your mesh is very coarse, you will have a lot of change, and every time you refine the mesh the result is changing. But from a single point you will see that even making the mesh finer is not really changing the result. And this is the kind of mesh we're looking for, which is not impacting our results in the end of the day. And when we talk about meshing, it's very important to understand how meshing is working on SimScale. Because in the end of the day, your daily challenge is to make sure, or what will take most of your time when using CFD, is to create the mesh and make sure the mesh is appropriate in terms of quality and size. And so let's try to understand how meshing is working. And at SimScale, we're using a tool for meshing called SnappyXMesh. SnappyXMesh, it's part of the open source CFD package, which is also used in Formula One by some teams, like Mercedes is using it, but also by automotive companies like VW, Audi, and aerospace companies like Airbus. And usually meshing is really a big mess because you have the so-called you have an approach where you start to mesh, first of all, only the edges, then you create, based on the mesh of your edges, you mesh the surfaces and then the volume, which can take a lot of time. But with SnappyXMesh, we have a different approach, which is much more straightforward. And this approach is about like taking a mesh, morphing it, and adapt it to the geometry interested in. So let's go back to an example. Let's say we want to simulate the flow around such a car. And so the white body here is the geometry of the car. And what we do in the first step, we create a so-called background domain, which is like a body containing our wind tunnel, our virtual wind tunnel. And the very first thing we do is meshing this whole background domain with a uniform mesh, which is intersecting even the car. And if you just think about this background mesh, it will not help us very much right now because it's like a mesh for flow through rectangular geometry. And the idea now is that we have this background mesh and the outer surface of our car. And now we start, first of all, to refine the mesh. Everywhere we think we need finer elements for solving gradients based on user-defined refinements. Like we can refine single edges, we can refine surfaces. And once we have applied our surface and edge refinements, and the surface of the car, the surface mesh, is looking like we want to do it, we are deleting the inner part of the mesh by just checking where is the intersection between the body we want to mesh actually and our background domain. The next step now, we can even apply refinements to the volumes. And then we can, for example, refine, like here's the wake. And if you take a look at it, what do we do? First of all, we find edges where we think there will be a big gradient. Then we refine the surface. For sure, we need a fine mesh at the car surface because we're interested in the pressure distribution around the car. And the volume refinement can, for example, help to resolve wake structures. And once this is done, there's the final step, which is very important, called snapping. And now, automatically, this stepped mesh, if you think about it, this is not representing our real contour of the car, is snapped to the surface of our model, and this will give us a very nice mesh which was quickly generated and is of high quality. Don't worry, we will talk about meshing also more in detail next week, but this is the most fundamental thing you need to know to understand how our mesh is working. And then there's a final stage, which is also very important when you're dealing with external aerodynamics, which is about generating layers. And if you remember last week, René introduced you to the concept of boundary layer, which is defined as the part of the flow in the near of the surface which is in direct interaction with the wall because of the sticking condition of the flow at the surface of the wall, and where we have large changes of the velocity profile. And just give you an example. So this is the velocity profile. So the length of these vectors are representing the magnitude of the velocity in x direction, in this direction. And as you can see, the boundary layer becomes thicker and thicker, and also the profile changes. And if you think about how we meshed, if we would use uniform cells, we would need a lot of cells because we have a high gradient in y direction, but a very small gradient in x direction. And this flat cells helps to resolve this directional change of velocity economically, which means it reduces massively the amount of cells we need. And if you don't use flat cells, but standard cells, it will mean that you have to use very, very small cells in the boundary layer, which will result in a very, very large mesh you won't be able to solve. And if you don't use small elements, you will just have like one element, including this whole boundary layer, which will just give you one velocity value for the whole profile, and your simulation results will not be accurate enough. And what's the biggest problem, it's not only about the quality of your boundary layer representation, but if you calculate a wrong boundary layer, it will also have a big effect on the remaining flow around the car. So every time you want to do a realistic simulation of fluid flows and you want really to exactly calculate the viscous effects happening in the boundary layer, you have to use this flat element, this layer element. And very important, you should never apply these kinds of elements to inlets. First of all, you don't need them, and the second reason that it will have exactly another kind of effect which will make a simulation numerically unstable. And it's not only about using these flat cells, it's only about using the right flat cell height. And the reason is following. If we want to calculate this fluid boundary layer very accurate, we would need even a lot of flat cells. And therefore, scientists were looking for a more effective and efficient way to modeling what is happening inside the boundary layer. And 100 years ago, researchers started to investigate what is happening actually inside this boundary layer, and they found something very interesting out, that the dimensionless velocity in the boundary layer is a function from depending on the dimensional wall distance. So first of all, what means dimensionless? Dimensionless means that we're not talking like about, the consequence of dimensionless is that the quantities doesn't have any units anymore. So dimensionless value is like comparing a value. And this function, if we plot it on a logarithmic scale, will look like this. And if you take a look at the beginning, this is represented by this blue graph. It's a straight in our logarithmic representation. Don't get confused. It's not linear in reality, but it seems to be logarithmic. And it means that inside this viscous sublayer, you can define different parts, different part layers in the boundary layer. And there you have a viscous sublayer, buffer layer, and a lower region inner layer. And this viscous sublayer can be represented by one exponential function. And if you know this and you're smart, it means that you can put the whole viscous sublayer into one cell. And you just have to make sure that you use the right cell type. Then you have one cell for this area here, from here to here, and it will massively reduce the number of cells you use. And this allows you to use a so-called wall function, and instead of really resolving this complex profile with a lot of flat cells, you can just use one cell. Inside the cell, the wall function is applied, and it will give you also a good resolution of what is happening in the viscous sublayer. It's just two very important things. First of all, if you use a wall function and a velocity profile instead of calculating the viscous sublayer, the y plus value of the first cell needs to be between 30 and 300 depending on the turbulence model. So the dimensionless wall distance. And if you don't use it and you want to resolve it properly, still you have to make sure that your y plus value for the first cell is 1 or below. And these are the two possibilities. For sure, using a wall function will reduce a little bit the accuracy of your result. But even in professional motorsport, wall functions are still used because they give the bait trade-off between accuracy and computational time. Yes, and at the last part of the meshing, you can extrude this layer based on the surface mesh. Okay, there are also some other parts. Let's talk about initial and boundary conditions. As you remember at the beginning of the presentation, I showed you this last step of the CFD process where our partial differential equations are transformed into a linear equation system which is solved. And for solving this linear equation system, or for solving differential equations in general, you need boundary and initial conditions. To understand the initial conditions, you have to consider the fact that these equation systems are solved iteratively, which means we are calculating a first iteration, give us a result which is far away from what we're looking for, and we're taking this result as a new start vector and repeating it again and again until we reach certain convergence criteria. And therefore, you need for the beginning a start value. And you can imagine just initial conditions like as a gas solution that you provide to the solver. In the end, it's like the initial values for pressure, velocity for all your cells. And it does not necessarily need to be very accurate, but it's very important that this is as realistic as possible, the initial condition, because as more of these initial conditions are matching with the, let's say, final result we are expecting, as faster the simulation will happen and as less iterations you need. And so this is very important, but the good thing is for most of aerodynamic simulations, you can just, basically when you use SimScale, you just don't need to apply any initial conditions. You can use the default values. The only initial conditions which you should calculate by hand for the whole flow field are turbulence parameters of the turbulence model, but we'll talk about in some minutes. In contrast to that, the boundary conditions are describing what is happening at the boundary of your model and how your model is interacting with its environment. And in contrast to the initial conditions, which are just used for the first iteration, the boundary conditions are used during the whole simulation. And boundary conditions are something like at the wall, the velocity is like this, or the pressure is like this. And you can give fixed values, you can calculate values based on what is happening inside your simulation, and you can also apply boundary condition like zero gradient, which basically means I don't know the value, but but what I know is that the value won't have a gradient. And as I mentioned, to solve these equations, you use numerical methods. And The finite volume method is one numerical method we use, but this is only used to discretize our problem, and we need some more numerical method tools and algorithms to, for example, calculate iteratively the solution of our linear equation systems. But we also need numeric, for example, to interpolate values between cells and for a lot of other reasons. And numerical settings are like used to or let me click in a different way. Usually, on theory, numerical settings are not used to describe the physics and have no impact, let's say, on how you model a problem, but they can help or make the difference if you want to make sure the accuracy of your simulation increase in terms of numerical perspective, and also to increase or decrease is a better word, decrease the computational time. And at SimScale, most of numerical settings have default values, which should be fine for your simulation, but especially if you're doing a full car simulation, there are some default settings we will show you later you should use. Next very important point is called turbulence modeling. And I'm quite sure you have heard about turbulence already in the past. So what is turbulence? And to make it very short, turbulence is the kind of chaotic change of field values in space and time, which means usually we talk about, let's say, steady and unsteady flow. And a steady flow means that it's staying the same all the time, while unsteady is like changing with time. So a steady case would be, let's example, a wind tunnel where we have an object and we have a constant inlet flow velocity. And then we can use a steady state simulation. While for transient simulation, we need it, for example, if we would like to ramp up the inlet velocity of the wind tunnel. But that's not the full truth. Actually, there are no real steady state problems in the world. And everywhere where we have especially turbulent flow, even if it at the first view looks like the values are steady, they are changing all the time. And just imagine we would put like a device for pressure measurement, like a pitot device, somewhere in the flow field of our car. We would have a constant inlet velocity, and what we would see is that in every point we have maybe small but still existing fluctuations of, for example, velocity, pressure, temperature, and all other variables we are calculating depending on our exact simulation type. And resolving these fluctuations would be very computational expensive. Really, it would be a big mess. So what we do, and that's the point, if we would calculate really turbulence completely, it's still numerically, but if we would resolve it completely on all scales, on the large and small scales we have, it will take us forever. So instead, and this is called direct numerical simulation, and today it's maybe possible to do direct numerical simulation for a flow, two-dimensional, three-dimensional flow around a cylinder at a very low Reynolds number, but not for a full car. It's not possible. So we use turbulence models. And the turbulence model use following simplification. It just say, okay, we have an average value for every field value, and this average value, on top of the average value, we have a fluctuation part. And here represented by this red average value and this blue fluctuation. So what we could do now is like resolve these oscillations for all time and length scales. And as I mentioned, this is called DNS and would lead us to very high computational effort, which is not an option for us, even not for Formula 1 teams, by the way. But we can do something else. We can just say, this fluctuation is so small, and we are not caring for them. That will solve the first problem, but create a second problem. If we ignore this fluctuation, maybe it's not obvious for you right now, but trust me, and if you want to check it yourself, I can post a good nice article on the forum or send it to you by mail. But at the moment where we are not considering these fluctuations anymore, one quantity is missing, which means our equation system is not closed anymore and we cannot solve it, even not the algebraic equations. So we need to reclose our equation system again. And what we do is we are introducing a new physical quantity, which is not real world quantity, the so-called turbulent viscosity. And so instead of using the physical viscosity, which is existing of our fluid, we're using a new viscosity called effective viscosity, which is calculated by adding the turbulence viscosity and the physical viscosity. And this effective viscosity is now used in the momentum equation instead of the physical viscosity. And this now closes again our equation system, and in the end of the day we can calculate the turbulence based on additional transfer properties instead of solving all time and length scales. And very important, this is a major simplification. It's not generally valid, but for external aerodynamics, there is some turbulence model which are robust. There are a lot of turbulence models, by the way, using different approaches to calculate and represent this turbulent viscosity. And especially for external car aerodynamics, we have some turbulence models which are highly validated, which are robust, and which you can really use for your fluid flow simulation. And there are so-called 1 equation, 2 equation, even 3 equation models. And the difference is how many different independent equations they use to, let's say, describe and express turbulence. And if you think about this, turbulence is a process where kinetic energy is dissipated from large to smaller scales. So you have large eddies at the beginning, and these eddies are like breaking up, becoming smaller. And so this is the way how kinetic energy, as I mentioned, is dissipated. And in industry, we are using most of the time 2 equation models, which have 1 equation which is representing the energy in the turbulence and 1 the dissipation rate, so how it's dissipating. And for all external CFD simulations on SimScale, we recommend to use the K-omega SST model. And it's the 2 equation model which is basically combining 2 of the best words. It's a mix of the so-called K-epsilon model and the omega SST model. And omega is a specific dissipation rate in the near of the wall, while epsilon is a turbulent dissipation rate in the free stream. So this, and the good thing is, the omega model, where you use omega for describing the turbulence, is very good for the specific dissipation rate near of the wall. So while the epsilon model gives you better values for the turbulent dissipation rate in the free stream. And so this K-omega SST model is automatically switching between those 2 models and uses an K-omega approach in the near of the walls and a K-epsilon approach in the free stream. And when you use this model, you have to provide the solver with 2 values, a value for K and for omega. And since K and omega are field values now, you also have to include them in your boundary and initial conditions. And usually, you don't know them, but you can calculate the turbulence of your flow at the inlet, for example, with some formulas. But the good thing at SimScale will show later to you that you just need to calculate, let's say, this turbulence parameters based on the Reynolds number, and everything else is calculated automatically, but we'll talk about this soon. Okay, and let's see if we already have some questions which I can answer. Okay, the first question is by Sumete, and he wants to know what is the exact significance of the wall function. All right. It seems like you asked this question some minutes ago, but let's go back to the slide, and I will try to make this clear for you. So, with significance, you mean the accuracy, Sumet, or something else? Okay, he's not answering, so let me try to answer this question like I got it. The reason why we need this, that otherwise we are not able to resolve the boundary layer completely, especially the viscous sublayer, with a very fine mesh, because this would lead to very, very large mesh sizes, which are difficult to handle. And the wall function is adding a big value to CFD simulation, because it enables us to get a very accurate approximation of what is happening in the viscous sublayer by only using one cell and this logarithmic dependency between dimensional velocity and dimensional wall distance within this viscous sublayer. Yes, Tusha wants to know if I can elaborate on different turbulent models like K, epsilon, K, omega, etc., and in which condition we can use the different turbulence models. Tusha, I hope I answered already your question, but let me tell it again. If we talk about two equation models, the K epsilon model, based on the specification, is very strong when we want to model turbulent, we want to model what is happening inside the free stream. But if we want to understand or calculate what's happening in the near of the wall, we need K omega model, which is better. And the K omega SST model is combining both models and automatically switching and using a K omega model in the near of the walls and a K epsilon model in the free stream. Then Vinaka wants to know if SimScale also supports large eddy simulation. Yes, we support LES simulation. However, LES, and those for you which don't know what it means, LES means large eddy simulation, and it's something between DNS and a turbulence model. So you do a direct numerical simulation for large scales, and for smaller scales you use a turbulence model. And we have even some examples, projects with LES in our library. However, for automotive application for more students, I would not suggest to use LES. It won't help you. Alejandro wants to know how many different mesh options we have. We have basically a hexa and a tetra mesher, but for complex geometries we would suggest, or I recommend, to use our hex mesher only. Okay. Right. I see there's some more questions and I will answer them later, but now let's try to continue a little bit with our today's curriculum. So one thing which is missing, a very important component, is the solver. Basically, solver is a very, let's say, large word, because solver includes technically everything which is used to solve your equation system. And the good thing is at SimScale we have a dedicated solver, let's say, for external aerodynamics, and you just can use the solver by default, and you just have to choose, for example, if you want to use the solver which for turbulence or for laminar flow, etc. However, there are some aspects regarding the solver I would like to talk with you also about today. And one thing is radiator modeling. This is not really related 100% to the solver, but in the end of the day, the question is if your solver is supporting this modeling technique or not. And the reason why we need radiator modeling is that we have actually radiators in our cars, in the side pods. And one option would be to completely mesh the radiator. But if you think about it, a radiator is very, very small, very small structures, which would lead us in a very huge mesh, which we could not be able to solve. So if you want to do a simulation of a radiator, usually just take a small sample and do a small sample for the of the radiator simulation. But if you want to consider the effect of the radiator on your flow in a full car simulation, there is a good turnaround using the porous medium modeling capabilities of SimScale and the so-called Darcy law. So what we're doing, basically representing our radiator with the porous zone instead of modeling it as a part. And the Darcy law is nothing more or less than a relation which is giving the dependency of a pressure drop through a porous zone depending on the volumetric flow through the zone. So if we have a radiator, like we are just measuring like how large the pressure drop is depending on the inlet mass flow through this radiator, which is equivalent to a flow. And what we're doing basically is, we just need two things to describe a radiator based on this model. First of all, we need to somehow describe this curve. And for this, we use a polynomial fit of second order. So, and if you think about these polynomial functions of second order, they are looking like this. A multiplied with x squared plus b multiplied with c, with x, sorry, not with c. It was too quickly. Plus c is 0. Or is a function. For inlet velocity or mass stream of 0 kilogram per second, our pressure drop is 0, which means that c is 0. And then we just need to fit the function and take the values for a and b. And the next thing we have to do is to calculate a local coordinate system. And this local coordinate system is describing like the orientation of our porous zone inside the car and compared to the global coordinate system. So let's say this is our radiator in the side pod. The free stream is coming from the right side. Then we have to give vector E1 and E3, and these two vectors are completely describing the coordinate system of our porous zone. And this can be calculated in the CAD tool. And basically, the only important thing is to scale this vector, that they become vectors with a magnitude of 1. And then we can just provide the CFD tool with these two vectors and with A and B for all 3 different directions. And then we have a model for our radiator. And another very important point between radiator modeling is wheel modeling, since our wheels are rotating. And one option would be to use really a rotating mesh, which means we have to do a transient simulation and which will add a lot of complexity. Another solution is to use, again, advanced modeling techniques. And one thing we can do is using rotating wheel boundary conditions and a multiple reference frame approach. Rotating wheels means that we apply a boundary condition to the surface of our wheel and the rim and all the parts which are rotating, where the velocity is, actually the velocity is 0 on the tire. But since it is rotating, we have at top of the tire another velocity at the bottom of the tire. And this rotating boundary condition is helping us to model the fact the wheel itself is rotating. But if we only rotate the wheel, we won't cover the effect of swirling inside the rim. And therefore we use a so-called multiple reference frame, which means we create a cell zone inside the rim, and inside the cell zone, here you can see it. It's a cut through the mesh of the wheel of a full car. And here you can see like this is the inner part of the wheel, and inside this inner part we put this rotating zone. And in this rotating zone we don't need to rotate the mesh actually, but we will add the forces and which are happening through this rotation artificially to this zone, and this will help us to model the effect of rotating parts, especially the wheels, much more better. For sure, using a dynamic mesh where the parts are really rotating is maybe more accurate, but again, for a full car this is so complex that usually it doesn't make sense to do it, because the gain of accuracy compared to the effort is much smaller. Okay, then we have some more questions. Bart wants to know if the software only use mass and momentum equations for computation. This depends on what you're simulating. If you only do a so-called cold flow simulation, where you assume that the changes of temperature and density are so small that you can neglect them, then yes, you don't need the energy equation. But if you want to do CHT or also like investigate how heat is transferred inside the fluid, then we use another model where we have 3 equations, including also the energy equation. Then Tusha wants to know, how do we optimize a duct for a radiator? Yes, and this is something I will show you. Let's talk about this in 10 minutes. Panka again someone wants to know, Pankjai wants to know how fine the mesh needs to be for DNS simulation and how to calculate the length scales of smallest eddies. Okay, first of all, the fineness of the mesh for DNS depends on the Reynolds number, but it's really, really small. So for a simple airfoil, let's say, we will talk about micrometers of edge lengths. And therefore, DNS is not an option. Even big Formula 1 teams cannot do DNS for a full car. It's just not possible. And then Jakob says a question related to the homework, that some of them have problems with loading the results, so they can't finish their homework. So what should we do? First of all, Jakob, thanks for pointing this problem out. I want to talk about this also later, but let's do it now. So we had a small problem this year. We had again much more registrants for this workshop that we ever expected. And as you know, SimScale is cloud-based, which means basically we have, in theory, unlimited computation capabilities which our users can use through the web browser. Today and yesterday we had the problem that a lot of people, like 100 people at the same time, tried to load this quite large CFD simulation to the post-processor, which made the post-processor quite slow. But we are already aware of this problem, and therefore we will extend the deadline, and don't worry, nobody will miss this deadline or fail for the homework because of technical problems on our side. Michael Smith wants to know what MRF stands for. MRF stands for Multiple Reference Frame. All right, so yes, and now it's time for our live demo. And we will now try to adapt what I've told you and do it inside SimScale. So let's start. And today we are doing what you're looking for. We will set up your very first simulation of a full car. And just to make it clear, the setup we are showing you right now is quite good. And actually you can use this very, very, very nicely as a starting point for your own CFD setup. And yes, so what we are going to do today, we're simulating a half car, since it's symmetric, on a straight line flow conditions, so a kind of virtual wind tunnel. This is the car. Around this car we have our fluid domain box, and the car is touching the floor, and the colors are representing different kind of boundary conditions. So the red face, red face here. This is our inlet. And at the inlet, let's say this is our coordinate system with X, Y, and Z. Ux is defined, for example, Ux is 20 meters per second. Y, the other components are 0. And this is our first boundary condition for velocity, by the way. And the pressure here is unknown. Here it's exactly the different way. Here the velocity vector is unknown, but we know the pressure here, it's the atmospheric pressure. For this wall we use a symmetry, which means that we have no gradients here. The blue wall is a slip-free wall, which means that since this wall in reality is not existing, we're just doing like there is no wall, so here's the velocity. And here for the floor we also use a moving wall, because in reality the car is moving through the air, so if you make the floor moving around the car, also the floor has to move. Tusha has a very good question. You're a very, very brilliant one, Tusha. He says sometimes the rear engine is not symmetric about the center. How much difference in results can be expected if we simulate half-car simulation with symmetry? Tusha, very good question, and this is one of the first things I will do. You cannot quite answer this question in general. If the engine is a little bit unsymmetric, maybe the impact is very small, you can neglect it. If it's a big unsymmetry, you maybe need, or you're forced to do full car simulations. And if you want to answer this question for your case, the first thing you have to do is do a symmetric simulation, do a full car simulation, and compare the results. Then Hermann wants to know why P and Px is 0. Px is nowhere 0 because there is no Px existing, Hermann. P is a scalar. And if you want to know why P at the green surface is 0, the reason is that P, it's our environment pressure, PO. It can be 0, it can be 1000, 5 million, does not care. Because pressure is about pressure differences. But if let's say, if you want an understandable example, P0 on Earth is around 1 bar. And Rishav wants to know, or says, there will be vortex generation due to open sites, hub upright area. From which boundary layer across it's passing coming from front? How do we simulate that if we mention the area as MRF zone? Rishva, I don't get your question completely. Can you please describe it a little bit more in detail, and I will try to come back on this. Okay, then there are some more questions related to this. Don't worry, guys. We'll talk about it at the Q&A, but now let's go further a little bit. Okay, so let's start to set up the simulation. What do we have to do? We have to do, first of all, the pre-processing, which means we have to mesh our car. Then we have to set up the simulation, and then we can do the post-processing. Okay, so let's switch to the SimScale platform, and then again, I've prepared something for you guys. So this is a project containing the geometry of a full car, of a half car, sorry. So let's open it and take a look at this model. So this is our model, which was prepared for the simulation before in the CAD tool. And there are some things which are very important. So first of all, we uploaded this car as a STL model. STL is a file format which was originally developed for 3D printing, but it's a very good one for CFD simulation because it gives you full control over the tessellation of your surface. And using this STL model can, depending on the CAD tool you're using, can be a little bit annoying sometimes. So in the fourth session in 2 weeks, we will show you and talk about how to create these models very quickly and effective. So if you ask yourself how to make the CFD suited model based on your design CAD model, don't worry, we will talk about this at the last session. First of all, let's just take the model as it is. And as you see, the model was grouped into several sub-solids, which makes sense because it makes it easier to set up the meshing and simulation. And it's made here a lot of so-called solids. And if you take a look, all of the parts are closed. So the driver is a kind of closed volume. The front tire is a kind of closed volume. And if you, for example, take a look here at, let's say, the suspension, you can see that it's basically intersecting a little bit. And that's not a problem as long as every of these patches is closed. Okay, and now let's set up the mesh. This is basically quite straightforward, but since we already 1 hour in the session, I will maybe make it a little bit quicker than last time, but don't worry, again, we will provide you with a detailed step-by-step tutorial. Then 2 questions by Sumde. First of all, how good is IGES model for CFD compared to STL? And the second question is the model solid or a surface model? First of all, It depends. SnapHex Mesh is based on STL files only, so it needs to use STL files for meshing. It cannot process IGES models. You can also upload IGES or STAP models, but then this model will be converted into S2Ls automatically. And this automatic conversion sometimes is not perfect. And therefore, that's the reason why we recommend to create the STL on your own in a CAD system. And this model is STL model, just in theory, is never a solid model because it's not supporting the concept of a solid. But still the model itself, which we use to export the STL, this should be a solid model. In the end of the day, it needs to be watertight, right? Because if you have a small hole, let's say in the wing, the flow would go inside your wing and give you wrong results. But as long as it's watertight, it's good. But usually, if your model is watertight, it's also a solid in most of the CAD tools. So let's start to set up the mesh now. And like last week, we first of all have to choose the geometry you want to mesh. Click on Save. And now we can add a new mesh operation. And again, we will use hex dominant parametric. Click on Save. And the first thing we have to do is to define our background mesh box. We define it by giving two opposite points of this box. And I will just enter the values we want to use and explain maybe some details because sometimes people get confused. So first of all, if we now create this box, you can see what makes sense. The box is matching with the lower part of the tires and with the symmetry plane. And if you take a look in Y direction, you can see that our minimum point is not 0, but 0.001, which means 1 millimeter. That's a first very important trick. If you use numerical models, you should not rely, let's say that's 0 is 0. You know what I mean, because it's working with finite numbers here, and just using this small gap will make sure that the model will be tight. And the same, and we have basically the element edge length, 7.2 meters in Y direction, 7.2 meters in Z directions, and around 27.825 meters in X direction. And the next thing we do here is defining the size of our base mesh box by giving the number of cells we want to divide this bound mesh box in each direction. So this box for the base mesh box will now be defined in 105 let's say pieces in X direction and 30 pieces in Y and Z direction. Okay, click on Save. And now we have, first of all, if we show the background box again, we have to define the material point, because later, based on the material point, the mesher decides if the outer part of the mesh will be kept or the inner part. And this base mesh box just needs to be a point inside the domain you want in the end to keep. So in our case, it must be somewhere between the outer surface of the car and the bounding box. And one point which is there, for example, is 0.25. The point is here, and this point is now inside the box but outside the car. And now let's start with some refinements. The first refinement we will create is for the surface. And the good thing is that we can now control the mesh fineness of different parts of this cars by defining different refinements. So let's define one surface for the body, the diffuser, the end plates, and the suspension. We will do a surface refinement here, level 5 to 6, which means the cell will be splitted up between 5 and 6 times, referring to the base mesh size. We don't want to create a cell zone, and we just apply it to weight. We have to choose assignment mode to faces, and then we will apply it to our diffuser, to our driver, to the front wing end plate, the inner and outer one, to the rear wing end plate, to the support, the upright, and to the body of the car itself. you can check here which parts we've selected. Just click on Save, and this refinement was added. We will now add also a refinement for the other surfaces, because if you don't define a refinement for a surface, it will just keep the base mesh size. For the wings, the wheels, tension, and for the bars, again, surface refinement. Here we need a little bit finer mesh, and then, for example, at the wings, for the small bars. Basically, you need a fine mesh in the case if you have large gradients or if you have a small geometrical structure. For both, basically. For the front suspension, for the rear suspension, for the front tire and the rear tire. Okay, now we will create another surface refinement for the wheel, hub and tire contact patch. 7, this is like ultra fine, which will be applied to the contact patch of the tire. Oh, I think I made a small mistake. Wait, we apply it here. Here we need a small mesh. And here we can remove this one again. And I forgot here to mesh the radiator support, which is the duct. Right. Then some refinements are missing. So for the side pot we also want a different mesh size, which can be a little bit more coarse. Add it here. And now we will add the feature refinement for the edges. And here we are in the end defining different levels for depending on the distance to the edge. So 1 millimeter away from the edge we want a level of 8, and 5 millimeter we want a level of 6. Right, now what is missing? So we need to add, first of all, now for the porous zone, we can now create for the porous zone, call it radiator. It's again a surface refinement for the radiator we want to use, but this time we want to create a cell zone. It will be created inside this volume. We have the same for the MRF zones, MRF front. We need it for the rear wheel too. And if you think about it, two things are missing now: region refinements and layers. So let's add region refinements. Region, you can call it region, this refinement. And let's add 2 new Cartesian boxes. The first box is here. And another box now we have this refinement box around the car for the wake. Can just choose them, apply cell level 3. And finally, we will add the layers. First of all, we will inflate a boundary layer on the full car. So let's select first of all the full car, but we have to delete it for some parts, including the MRF zone, so we don't want a layer. Radiator. And we don't want it on the red support because it will decrease our mesh quality. And since the wheel is in a part, the flow velocity is also real, we can just ignore it. And these settings now describe how this layer should be sized. And these parameters have a big impact. And we just calculated values related to these settings, which should work for a Formula Student car at around 20 meters per second. But don't worry, we will also show you during the next sessions how to calculate the values on your own, or you can also just modify them and test until you get the right results. So now we added layers to the car, and we will also add layers to the floor, which is moving. Here we need bounding box layer addition for Z-min. Perfect. And now everything is defined. The only thing we have to change is we need to use more processors for this large mesh, and we also can optimize some of these meshing parameters for making the mesh generation faster, but this is something you will see in the tutorial. Yes, the same values you should use for, let's say, all meshing. And since meshing can take some time, I have for sure prepared something for you guys, a project where I've already finished the meshing. Once it's loading, let me just see if there are some more questions. Okay. Brandon has a very interesting story to share with us, and he can remember on an analysis of an old F3 car he did with side intakes. You maybe know with this old Formula 3 car have the air intake here on the side, and they basically found out that they can still use a half model since the wake of this intake is mostly gone and didn't interact with the rest of the car. Brandon, thank you very much for sharing this insight with us. And just because a lot of people are asking, what should I do if the car is not symmetric? If your car is not symmetric, for example, if you just have one radiator, like Zhang asked, you can't do a symmetric simulation. Or you have to be aware of the simplification and evaluate it before, like Brandon explained. Well, so many questions, guys. Let's see if... Okay. Right. We'll answer some questions later. And once the mesh is generated, it can take up some hours. And in the end of the day, you can see this mesh contains 8 million cells. And this is how the mesh looks like. This is our mesh, and now it's still loading. It's quite large, so don't worry. And once it's loaded, we can rotate it also. Okay. Some people are asking questions like, why is the refinement at this part finer and for this part more coarse? it was basically what we did is we started to do a simulation which was very, very fine, and then decreased the refinements until we saw that the results starting to change. And from our experience, this kind of setup is the like minimum viable setup if you do formal student simulation, aerodynamic simulation with SimScale, but for sure later you are free to modify the settings. But don't forget one thing, just having a large model is not making a simulation good. Okay, now the mesh is loaded, so let's first of all rotate it, wrong direction. And now we can take a look at the mesh from the side. So here you can see he makes it smaller. Here you can really see like how the mesh is looking like. It was refined in the near of the wings. Let me hide everything else except of this symmetric plane. And if we zoom in, we can see, for example, the layers which were generated around the wing or around the body. And this is very important. Right, and what we can also see is we have now 4 different mesh zones. We have one mesh zone like containing the fluid around the car, and then we have one mesh zone for each MRF in the wheels, and we have one cell zone for the radiator. By the way, these cell zones are closed, but this is just a question of presentation why they look open, because here we have the interface. So here it's like in contact with another part of the mesh, and therefore it's not visualized as a closed body, but it's a closed cell zone. So now we can also take a look, for example, at the surface mesh of the car by hiding the bounding box. And so let's maybe remove or change the representation, and this is like our CFD model without the edges, but if you zoom you can see that there is like small difference compared to the surface of the CAD model. Alright, so now let's set up the simulation. It's basically the same like we did last week. Just the only difference is that our UI changed a little bit during this week, so don't worry. First of all, you have to choose what kind you want to simulate. In our case, it's fluids dynamic and incompressible simulation. Why incompressible? Because we can assume flows under 300 meters per second as incompressible. So click on Create. Now it's asked you for a name for the simulation. Let's say FSAE CFD. The turbulence model use K omega SST by default, and also the other values you just can use the default values. We want to do a steady state simulation and use a simple solver. Next step is to use the mesh. We only have one mesh, so we can add the mesh we've just created. It can take some seconds again, and then the mesh is loaded and added to our project tree. And yeah, the next step is now to define which material we want to use. So we click on New Material. We have and now we can, let me zoom out, add some materials. And we need now to add, first of all, we can import a material from our library. In our case, it's air. And now we can just use air, like here, click on it, it will be added. and the properties will be imported, and then we just can choose all cell zones. Okay, initial conditions, as I mentioned, just use the default values. The only values you modify is for K and omega for the turbulence model, and we will upload the formulas into the forum how to calculate these values, which are depending on your car length, the velocity of your test, and the viscosity of the air, so the air temperature. Well, and now we just need to define the boundary conditions and the advanced concept modeling for the MRF and the porous zone, and we are nearly done. So let's change the representation to surface and start. We have an inlet here. We have an outlet here, just choose pressure outlet type. For the side walls, top and side wall, this and this one, we just use a slip wall. For the symmetry, here, we just use the type symmetry. For the floor, which is moving as I mentioned, just use wall, moving wall velocity, since this is a translational movement. And three things are missing. We need at least one boundary condition for the whole car except the tires themselves, the wheels themselves, because there we want to add this rotating boundary condition. So let's see, where can we see the wheels? Front tire, rear tire, and if we know, take again our selection box, just choose wall, no slip wall function, it's fine. And finally, for our front tire and the rear tire, the front tire, we need a rotating wall boundary condition. So front wheel, it's then a wall, a rotating wall velocity, and here we just have to describe the rotation by giving the origin and the axis of rotation. So for the front wheel, it's minus 0.41566. And it's in y direction. And the angular velocity, you can calculate it. It's based on the diameter of your wheels. And the inlet velocity, it's minus 90.9. And regarding the direction, you just have to use the right hand rule, which you also know from Lorentz forces, for example. Right, that's good. And then we have to just apply it on a face here. Can do the same for the rear wheel. Copy the boundary condition, choose another wheel. We just need to change the center and basically only the x value. Let's rename it rear wheel. And now we can create the rotating zones for the front. The same game. Now we need to create also one for the rear wheel. Oh, I just mixed it up. So this is the rear wheel. And this is the front wheel. It's the same coordinates, like for the rotating wall for sure. We have to assign it to the front wheel. And the final thing is the porous zone for the radiator. Here we choose radiator zone. And then we have first of all to enter the vector, which I calculated through my CAD system. So it's the next component is and we have in the end enter the coefficient, so it's for sure it's 0 in all the other directions, and these values are depending or referring to this coordinate system, since the radiator is like it can only flow to the normal direction of the radiator. Okay, now we are done. And here we can adapt some numerics, and we can also add some result control items, for example, to calculate all the forces acting on the car. We can also do it based on several components. And finally, we just have to set up how many iterations we want to run, how it should be saved, only the final result, how many processes we want to use, and what's the maximum runtime. Now we can just go on, create a new simulation, and that's it. Well guys, we're running out of time, so let me quickly show you how the final simulation will look like, the results. And let's open it here. And once you've finalized the simulation, it can take some hours. You will get notification by email, and this time it took nearly 3 hours. Then we can take a look first of all at the convergence plot and can see like the residuals converged. You can also take a look at the forces. Also became stable, and we can take a look into the three-dimensional solution field. And for this large simulation with 10 million cells, it can take up to 3-4 minutes until everything is loaded, since the data needs to be transferred somehow. Let me just show you some impressions I've prepared, and then I can also give you a short demo how to create these images using the post-processor. Well, so the first thing you can see here right now is a slice of the total pressure in y direction. And so here these colors are representing the energy of the flow, and red means it's a high energy flow, like undisturbed free stream flow, while green and blue are representing wake. And now let's take a look at some key results. So for example, this is a slice showing the pressure coefficient through a y plane in the near of the radiator. So here you can see front wing, rear wing, this is the side pod ducts, here we have the radiator and the front and rear suspension. And the first thing we can see that we have stagnation points. everywhere where this like free stream is hitting the object for the first time. And one stagnation point is like on the wings. And at the stagnation point, the pressure coefficient is 1 because all the kinetic energy of the flow is converted into pressure since the velocity, since it's stopping to move. And we have low pressure areas behind the devices, and in this low pressure areas basically are used to generate downforce in that direction, and they also have impact on the drag in x direction. If you would integrate the pressure field on the surface of the car in x direction, you will receive the drag, and if you do it in that direction, you will receive the total downforce. So now let's take another slice, which is in the knee of the symmetry plane. And now we're taking a look at the velocity magnitude. So in red means a high velocity, and blue it's a low velocity. And first of all, you can see how the wing is working. Like the flow is accelerated under the wing due to the curvature, and this acceleration of air means that the energy is dropping, and in this case the energy is the static pressure. And if you take a look, low pressure area, high velocity area. And everywhere we have fast changes in surface direction, we get a flow separation. This is, let's say, body-induced or shape-induced flow separation. But flow separations can also happen due to pressure gradients, like the flow separation on the top of a wing, which René explained last week. And if we take a detailed look at what is happening at the wing, you can directly see what in effect that was explained by René, that he used the stepped wings as multi-element wings to prevent flow separation by bringing new fresh energy to the boundary layers through these gaps. Now let's take a look at the modeling of the radiator. And you know what you can see here now is basically we do two simulations. The upper one is using the porous media approach, and the lower one is not using the porous media approach. And on the left side you can see a plot of the static pressure through the radiator. And in the case we have no porous media, let me just maybe quickly draw it. So we plotted how pressure is changing on this line. And you can see the red one, the blue one is representing the pressure without a porous media, and if you don't have a porous media, you basically have a small pressure drop, but which is more related like to the shape of this duct. It's like a small diffuser, and therefore we get a small pressure drop. But if you have the porous media like here, you have a massive pressure drop like in reality. The one effect is the massive pressure drop you have in this radiator, which means it increases a little bit the back pressure in front of the duct. And if you compare it, one result is also that the pressure increases a little bit, decreases a little bit behind the radiator, and therefore also the influence on the rest of the car. And here you can see like the overall effect. So if we take a look at the wake behind the car, again we're taking a look at the total pressure. You can see having a porous media is really necessary to model the pressure and energy loss inside the duct correctly, and for sure this has an impact on the overall flow structure. So using a porous media or modeling the radiator is not only a question of the accuracy of what is happening in the duct, but also it has an impact on the full flow topology. And since the air is leaving the duct with much lower velocity and a lower pressure here, it changes the overall flow topology, as you can see. And for sure the porous media or the radiator will also increase a little bit the drag. Yes, now let's take a look on it from above, and here you can again see the velocity distribution, like how the air is decelerated through the porous media if or through the radiator if you use the porous media approach. So you will have more stagnant flow and more drag. And if you don't have a radiator, it's just like an opening, a bonnet, and you have much faster flow in your rear region, which has a big impact on your rearing flow, by the way. Now let's take a look on something very interesting, that basically the porous media is even impacting the flow around the front wheel. That sounds maybe strange, but it makes sense for sure, because if you have here, let's say, a higher resistance, for sure, it will also change everything which is happening upstream the flow. And if you take a look here, it's like really changing. If you have porous media, using a porous media approach and modeling the radiator, you have a much larger wake and the end plate, and therefore it's also, and the funny thing is that this decreases the size of the wake in the knee of your tire, and that really shows how everything is depending on each other when doing external aerodynamics. And very interesting, I like it. And don't worry, next week you will learn how to use these results to improve your car. This week is really about being able to generate such a simulation. Now let's take a look at the impact of MRF. So on the left side we have this multiple reference frame, on the right side not, and it's obvious. You can see that the swirl effect inside the rim is much larger using MRF. And actually, if you compare it with other simulations where you just take a look at the wheel and use dynamic measures, you will see that MRF is adding basically too much of a swirl. But it's still better than having no swirl at all with not using MRF, and the results are quite realistic. And this is very important if you want to optimize like brake cooling. I know in Formula Students not very important, but you need to have realistic flow conditions in your wheels, and for MRF is a big help. You can see like it's much larger, this low velocity area. Now again, the wheels, MRF versus no MRF, and now a different view. Now we look from the Y direction, and you can see like how the whole flow structure in the rim changes when using MRF, especially between the spokes. And here, for example, you have separation at the spokes because the flow is like, the wheels are like not moving. But if the wheels are moving, you have no separation here. And now let's just compare it. There are 4 different simulations. The left upper corner is what I showed you, including MRF and porous media. Right is without MRF. This one is without porous media, and this is without porous media and MRF. And you can see like there are like differences in the results, especially when you take a look. Effect of porous media is marked in magenta, like here's a wake of the rim. And the effect of MRF is more at the other side of the rim. And yes, for example, if you compare this one and this one, you can see that the wake is slightly thicker when you use this advanced concept modeling, which means not using this concept would give you too low drag values. Guys, I know this was quite quickly, but we are again running out of time, and all the slides are in the forum where we can discuss these aspects. Now I would like to show you homework. So your job this week is to perform exactly this kind of simulation on your own. Again, we will provide you with a step-by-step tutorial, with a recording of the session, and with support through our forum. And we will send you tomorrow an email including all the resources for that session, the recording, the tutorial, but you can also find it on simscale.com/FSAE, and there you can from tomorrow on access all the resources. And yes, we're looking to a lot of homework submissions, and now I think we're really running out of time, but let's just answer some questions, and those questions which were not answered, please reach out to us using the forum if it was not answered so far, and we will come back on you. So Bart wants to know, how is the result calculated if it's an unsteady flow? Yes, Bart, we did also an unsteady simulation of the car. The results are slightly different, not very much. Due to the limit of time, we were not able to include this to the session, but if you're interested, I will see if it's possible maybe to make a blog post out of it. Just because of people are asking, yes, we will extend the submission deadline of homework 1 due to the overload of the platform, and you can get some more days to solve it, and don't worry. Then, let's see. Rolo wants to know, what's about the size of the boundary behind the car? How wide should it be to avoid interference? Rahul, that's a question, again, depending on your simulation. For a Formula Student simulation of a car at 20 meters per second, the bounding box we are using is absolutely fine. The best thing you can do is, first of all, experimenting, like test different bounding box and see if there is still effect. And what you can also do all the time is like using boundary conditions, like the slip ball boundary conditions are used to minimize the effect of the walls. Then some people asked that they had problems with technical problems. In the case you have technical problems related like you cannot open the platform, it's really not even loading, you should directly reach out to our support team, support@simscale.com, or write it into the forum. Some people asked what if they can resubmit the homework in the case they found an error. Yes, for sure. You can resubmit your homework as often as you want. And one thing, if for those of you who registered after the first session, if you want to access the first webinar, you have to take a look yourself at the forum or the website, since your email was not included to the addressee of the email. But I will try to find out if we can maybe resend the email to those of you who registered after the first session. Again, you will have 1 week time to solve the simulation, but if you need more time because of technical problems, just let us know and we will find a solution. I see there are so many technical questions and I would like to answer all of them, but we're running out of time. We will go through these questions after the session and try to answer some of them next week. And if your question was not answered, because sorry guy, I don't have any overview, like 100 of questions. If it was not answered, please feel also free to reach out to us using the forum. Guys, thank you very much for your time. Again, we spent nearly 2 hours. I promise you next week we will stay under 90 minutes, but I hope it helped you. Just in the case, if you are not sure about everything, rewatch the recording, and yes, I hope to see you next week. Then we will have Torbjörn Larsson with us, who is the former head of CFD at Ferrari Formula 1, BMW Formula 1 and Sauber Formula 1, one of the most experienced CFD engineers I know. And yes, looking forward to it. Hope to see you next week. Wish you a nice week. See you soon. Bye.